Hello everyone. Today I am going to discuss momentum, impulse, pollutions, and center of mass. Let's start with momentum. In case of applied force, which is not complicated, we can easily use Newton's second law of motion to describe the situation. But in many situations, such as a bullet hitting a carrot, we cannot use Newton's second law to solve the problems, because we know very little about the complicated forces. In this part, we shall introduce momentum, impulse, and conservation of momentum to solve such problems. Let's talk about the assumption, or particularly the topics about momentum. Okay, the momentum of a particle depends on its mass and velocity. So figure shows here in two-dimensional case, xy coordinate system, the object with mass m is moving with velocity v, and the direction of the velocity is given by a particular arrow. Then we can define momentum by this equation. Momentum p is equal to mv. So the multiplication of mass of an object and the velocity of that object gives the momentum. And momentum is a vector quantity which has both magnitude and direction. The direction of momentum is the same as the velocity, and the SI unit of the momentum is kg meter per second, and also another unit of the momentum is Newton second. A particular value of the momentum can be achieved in different ways: a small mass moving at a high velocity, or a large mass moving with a low velocity. There is a particular relation between momentum and Newton's second law. Newton's second law can be written in terms of momentum as net force summation of force F is equal to differentiation of momentum with respect to time t, which is denoted by dp by dt. Momentum of a system. So we can easily calculate the momentum of a system by adding the individual momentum of the particles. Okay. So in figure A, there is a solid object contains some particles. Among them, two objects or two particles is denoted by I and J. And the momentum of object J is Pj equal to mj Vj, and the momentum of I object or I particle is Pi is equal to Mi Vi. Or particularly momentum of the other objects we can easily calculate by using this type of equation. Then the total momentum, which is a vector quantity, total momentum is equal to summation of individual momentum, summation of Pi. Here I denote the I1, 2, 3, 4, or particularly objects. Okay, this is equal to integration of Mi Vi. And in second figure, there are four objects: object 1, 2, 3, and 4. So the momentum of object 1 is P1 is M1 V1, P2 is M2 V2, P3 is M3 V3, and P4 is M4 V4. The particles may be pieces of a solid object or individual particles associated with each other. Okay, but the total momentum is always the sum of the individual momentums. Now let's see about the particularly relation between force and momentum. So assume the force and acceleration are constant. Then according to the Newton's second law, vector force is equal to ma, and according to the equation of motion, we can easily calculate the acceleration, which is vf minus vi divided by del t. Here vf represents the final velocity of the object, and vi represents the initial velocity of the object, and del t represents the time interval between this velocity change, or between the object between the force involved here. Okay, since momentum is mass times velocity, the force can be related to the momentum. So after solving this equation, we get net force on or mainly force vector into time interval del t is equal to mvf minus mvi. So mvf represent the final momentum of the object and mvi represent the initial momentum of that object. So final equation is pf minus pi is equal to force into time interval. So force into time interval, this is called the basically impulse, or also the change in momentum is called the impulse. So impulse is equal to force into change in time or particular time interval is equal to change in momentum. So this is the impulse theorem. So here from this we can say that impulse is a vector quantity. So impulse is a vector quantity and its direction is parallel to the total force. Now let's solve a problem related to this topic. A ball of mass 0.25 kg lands off a wall as shown in the diagram. The ball approaches at 15 meter per second at theta equal to 30 degree, which is incident angle, and leaves at 12 meter per second at phi equal to 20 degree, which is reflected angle. The collision lasts for 15 milliseconds. So first question A is, what are the components of the impulse experienced by the ball? And second question, what are the components of the average force acting on the ball? So if we try to find out the impulse, we can use force multiplied by the time interval, but the time interval or average force, particular force is not given here. So we have to use the second equation. The change in momentum is equal to the impulse. Okay. So impulse is equal to the difference in momentum. So I equal to, here I describe the momentum. So you can also use J, the momentum. So I represent the momentum is equal to, sorry, I represent the impulse. Okay, so impulse I equal to mvf minus mvi. There first part is final momentum and second part is initial momentum. So this is a vector quantity, mainly velocity is a vector quantity here. So this is a vector equation, and to get components we consider the x and y components separately. So the x component of the impulse equation is ix is equal to mvfx minus mvix, where where vfx represent the final velocity x component and vix is the x component of the initial velocity. Okay, so after solving this component, the final velocity has x component 12 cos 20 degree, and the initial velocity has x component 15 cos 30 degree. So the finally the x component is minus 0.4285 Newton second. And if you try to find out the y component of the impulse, mbfy minus mviy is equal to 0.25 into 12 sine 20 degree, which is the y component of the final velocity, minus 15 sine 30 degree. So here minus 15 sine 30 degree is the y component of the initial velocity. And finally, answer is 2.9011 Newton second, the y component of the impulse. Then the impulse vector is equal to minus 0.4285 I cap plus 2.9011 J cap, and the unit is Newton second. So this is the impulse. Okay, and after solving this, we can easily calculate the average force involved in this solution. So we know that impulse is equal to average force into time interval, where delta is the particular give the time interval of the collision. So we have already calculated I, and we are given del t is equal to 15 milliseconds. So here average force is equal to impulse divided by del t. Then average force is equal to just given impulse okay, divided by 15 milliseconds. And finally, the average force is 28 minus 28.6 I cap plus 193.4 J cap Newton. Okay. Now the impulse and variable force. Okay. So first figure shows the constant force. So in case of constant force, if the time interval is given and the force value of the force is given, we can easily calculate the impulse is equal to F del T. Okay. But if the force is not constant, force started from the zero and increased at a certain point maximum value, then again decreased to zero. So the magnitude of the force grows rapidly from zero to maximum value and then goes to zero, decreases to zero. Okay. Then in this case, impulse gives the area under the force time curve. Okay. So if we draw the force versus time graph, then the area under this graph gives the impulse. But in this case is also impulse is equal to change in momentum. So this figure shows the particularly relationship between the impulse and the momentum, and also impulse in case of constant force and impulse in case of variable force. Okay. So here the last equation gives the impulse in case of variable force. So we have to uh, integrate from initial time to final time of ft, f del t, basically f del t. So the integration of f del t gives the impulse in case of variable force, but in case of constant force, figure 2 gives the constant force. So in case of constant force, impulse is equal to f into del t. But in case of variable force, integration impulse is equal to integration of time limit from t1 to t2 f del t, where f is a function of time. Okay. And in case of impulse and average force, just we have to use the impulse formula. In case of average force, impulse is equal to f average into del t, which is also equal to uh, this change in momentum. Here figure shows a graph, basically force versus time graph, and here there is two graph. Okay, so one is narrower and another is wider, basically wide graph and narrow graph. But if the area of both graph is equal, then the impulse involved in this case is also equal. So basically a large force with a short time and a small force with a long time gives the equal impulse if the area is remains same. Okay. Now let's solve a problem related to the variable force impulse. A particle of mass 2 kg is initially moving along the y-axis with a speed of 2 meters per second. At time t equal to 0 second, a force F in the positive y direction is applied to the object for 3 seconds. The force varies with time according to the equation Ft, here force is a function of time. So Ft is equal to 9t minus 3t square. So this is the basically force equation, where F is in newtons and T is in seconds. First question is, what are the units of the constants in the equation? So in this equation, constants are 9 and 3. So according to the particularly units, okay, we can say that unit of the force is Newton, then the unit of the 90 is also Newton, and also unit of the 3t square is also Newton. Then 90 is equal to Newton, so unit of the time is second, so 9 second is equal to Newton, then 9 equal to Newton per second. Okay, so the constant 9 has the unit Newton per second. In case of 3t square, so 3t square is 3 second square is equal to Newton, then 3 is equal to Newton per second square. Then the unit of the constant 3 is Newton per second square. Now question number B, calculate the final speed of the particle after t equal to 3 seconds. So we have to calculate the final speed. So there is a relation between the speed and momentum, and also there is a relation between the momentum and impulse. So we have to first find out the momentum, okay? Then we have to use impulse is equal to momentum. But we don't know the impulse, okay? So then we have to calculate the impulse. So impulse J is equal to integration of f dt, and the limit here is starting point is t equal to 0 second and end point is t equal to 3 seconds. So limit is 0 to 3, and fourth equation is 90 minus 3t square dt. Then integration of 90 gives the 9 by 2 t square minus integration of 3t square gives 3 by 3 t cube, okay, then t cube, and the time limit is 0 to 3. So this equal to 9 by 2 3 square minus 3 cube, okay, for upper limit, minus in case of lower limit, if we input the t equal to 0, in both case answer is 0, okay. So if you put the 0 in t square, answer is 0. If you put the 0 in t cube, answer is 0. And finally the answer is 40.5 minus 27 is equal to 13.5 Newton second. So this is the impulse, 13.5 Newton second. Now if you put this value in momentum, change in momentum is equal to impulse equation. So J equal to del P, then J equal to 13.5, which is equal to mvf minus mvi, which is the change in momentum. Then this equal to 2 into vf, we have to calculate the final velocity vf, minus 2 into initial velocity is given 2, okay. Then 13.5 is equal to 2 vf minus 4, and finally final velocity of the object is 8.75 meter per second.